Good afternoon, everyone. Thank you all for coming. And it's my great pleasure to invite Mopeli Kama to this session. So as you know, Mopeli has been a PhD student of the group for some years, to the extent that he's something of a founding member. Yeah. In fact, our association goes back to the UCT days where he studies his master's degree with me. And so after this kind of drawn out examination process, I'm pleased to say that the thesis has passed and the degree is confirmed, and Mopeli will soon graduate at the upcoming ceremony. What's the date for that, Mopeli?
On the 30th, this Friday.
This Friday, right, great.
Great.
Yeah. So today is a kind of victory lap here where Mopeli will unpack some of his findings for us. So please go ahead, Mopeli.
So my presentation is on the development of a computationally efficient monolith reactor simulator, a CFD hybrid model analysis of methane oxidation monolith catalyzed systems. I will just talk a little bit about partial oxidation of methane and what motivated us to study this system. Partial oxidation of methane, unlike processes like steam reforming, results in the lower hydrogen to carbon monoxide ratio. And this is suitable for most downstream applications such as Fischer-Tropsch or some alcohols synthesis. And also compared to steam reforming, it is less energy intensive, low cost. The designs in this case are compact, and also it leads to fast startups. However, despite these advantages that I have mentioned, there are some issues in that selectivity may become a major challenge because there is a complex interplay of total oxidation, which is and partial oxidation, and the total oxidation products are undesirable. So this complex interplay is something that needs to be gotten rid of. And also there is formation of local hotspot, and this formation of local hotspot may lead to catalyst. These are the challenges that partial oxidation of methane in monolith reactors present, and they need to be addressed. Now, when it comes to the modeling work of partial oxidation of methane in monolith reactors, it requires computational fluid dynamics studies. And we know that CFD is basically the solution of Navier-Stokes equations in digital computers. And the modeling of these systems is complicated by the complex kinetics in relatively complex geometries. And there is that spatial distribution of mass, heat, and mass transfer. Adding to that, also, there are numerous species to account for in solving the governing equations as in mass balance equations. So you maybe, as I can show you on this screen here, you can see that the monolith also, it constitutes many thousands of channels. And if you were to model the entire monolith, this therefore implies that there is a high computational cost. Now, the problem with modeling this as a single channel is that you may have a flow maldistribution at the inlet, and the hydrodynamics therefore will be different in each channel. Therefore, it is difficult to try to model this as a single channel. And when you model this system, the monolith reactor, you will realize that there is no mass transfer across these channels, but there exists this radial thermal gradients which result in heat transfer in thousands of channels. So you can already see that this is like a heat transfer problem. I have shown on the screen here the single channel monolith with a square cross section. And the local variation in the predicted variables in these monolith channels depends on the diffusion path length. And these local variations that I have just mentioned are difficult to capture when one uses one-dimensional models. So it is therefore required that 3D models are used. And also remember, I have spoken about the formation of local hotspots, which I said this may lead to catalyst deactivation, and this is undesirable. And in partial oxidation, the formation of local hotspot is one of the major challenges. Now, when it comes to now the hypothesis, the complex behavior that I've spoken about in monolith reactors can be solved by a coupling of a two-scale model. And this is through a linear combination of two analytical solutions. These two analytical solutions will be the analytical solution for the zero flow region and the free flow region. So now the approach that we used in solving this system is that we have the high-speed way of modeling monolith reactors by the hybridization of the pseudo-homogeneous approach with the multi-tubular approach. Then this will be clearer as we go through the presentation. As you know that now we have to validate the model results. So we used CFD as a numerical experiment and benchmark. And this we did, you find out the published data of CFD. So we took that and we validated it under same operating conditions to gauge whether our method works. And I must also indicate that as you use this pseudo-homogeneous approach, we had to adopt also the effectiveness factor approach. And this we did in order to account for the mass transfer limitations. And as a result of that, it means that the estimates for concentration in this case will be accurate. And as a result, the reaction rates also will be what? Will be accurate, hence our results will be accurate. Now on the effectiveness factor approach that I have spoken about that we employed, we have two cases here where you can apply this effectiveness factor approach in an isothermal case and in a non-isothermal case. And the first equation just shows the isothermal case and how the effectiveness factor is used in terms of including it in the mass balance. The latter part shows the inclusion of the effectiveness factor in the mass balance of an isothermal case. And you remember, as I said, this we do to account for those mass transfer limitations. Now, the hybrid model that I spoke about, which is the high-speed way of solving this complex problem, is just a computational efficient way of solving the governing equations in the multi-channel system. And in this case, we do so by adopting the pseudo-homogeneous approach. And and then these analytical equations, remember when I first introduced this, I spoke about two analytical solutions, which will be the analytical solution for the free flow and zero flow. And we used a linear combination of those two. And now the modified plug flow model for a single channel was coupled with those two analytical solutions that I spoke about, which we used linear combination. And we use that for heat transfer across the neighboring channels in the multi-channel monolith, because we have said that there is heat transfer across the channels. Now, the scale of modeling of this monolith reactors is twofold. So we have the micro and the macro scale. In the macro scale, you model the monolith as 1,000 of channels. And as I've said, in this kind of approach, the computational expense is quite high. However, if you adopt the micro scale, this treats the monolith as a single channel and leads to moderate computational costs. But before you can use this approach, as I've said, we had to combine this with the analytical solutions from the two regions that I spoke about. Now, the model equations that we used in this, as I've said, the Navier-Stokes equations, the continuity, momentum, the mass balance, and the energy equation. and those are for the gas phase. When you look at the surface species, the equation on the last part of the page there shows how the surface coverage varies. And this is the heterogeneous reaction as shown by RIH. And then this would be the surface reactions that I will show later and how they were modeled. And as I've said, now these are the equations that you have in CFD. You have to discretize this equation using various methods. And in this case, there is an efficient method that was used to solve this, which is called an operator splitting method. And it's quite efficient in the sense that it splits the reaction and transport terms, and it uses the appropriate algorithms for each. So this is the method that is quite appropriate in speeding up the calculations. Now, the boundary conditions at the catalytic wall for concentration, it's as shown, and also for the energy balance, it is shown, and this was also used in our calculations. Now, remember, when I first introduced this, I told you that there are many species to be accounted for in this kind of systems. And in this case, I've shown the reaction mechanism, and you have this at adsorption and desorption, and also the surface reactions are shown there. So this equation, these reactions that we have here, the accompanying surface reaction rate for all the equations that I've shown here is represented by this, which shows the heterogeneous reaction rates at the monolith reactor wall. So you can imagine if you have thousands of these species that you have to solve for in your chemistry and mass balance, it does show that you will have a computationally expensive problem to deal with. And you have to look at some efficient ways of solving this. So in CFD, first of all, you need to have a geometry. Remember, I spoke about some geometry and meshing. Now, for instance, in this case, in demonstrating, we have 25 channels. This is the geometry that you will have created. And now this is how you have this geometry and meshing is represented in this case. And the Navier-Stokes equations that I have shown in the previous slides, therefore, will be solved at each channel in the multi-channel scenario, as I've said, and in open form. But remember, in this case, we have transport and surface microkinetics. So what we needed to do was to use another solver for the microkinetics at the catalytic walls called catalytic form, and couple this with the transport equations in open form, such that, because previously there was no way that the microkinetics could be coupled with transport in open form, you would have to couple this with some other external subroutines. And given that we are dealing with some stiff equations, I had to look for some libraries which would solve these stiff equations quite efficiently. And I found this to be very efficient in solving these equations, which are stiff in nature. So when you mesh this, as I've shown, geometry and meshing, it is very important that the solution that you get at the end is Crete independent. So to ensure that you have consistency in the solution that you have, we perform the mesh sensitivity studies. And in doing so, you do this until you have the solution that is Crete independent. And this is what we did. And in this case, I've shown the results for the mass fraction profiles for these reactants and the products, and also the temperature of the catalyst and the temperature in the gas phase. So when your temperature no longer changes as you change the number of cells, or if you refine your mesh, then it does show you, or if your truncation error is 0, then you are sure that now your solution will be consistent. It's no longer Crete dependent. So this was the first step that we did before we can actually get into solving the problem. Now, when I talk about this, just a summary of the CFD modeling, and remember we said here it's partial oxidation. You have methane and oxygen to give us the main products of partial oxidation, carbon monoxide and hydrogen. And these are the two undesirable products I spoke about, carbon dioxide and water, which are the total oxidation products. So when you look at this 3D plots, you will realize that the radial gradients, they exist up to just 0.05 meters of axial coordinates. Beyond that, they disappear. And as well, after the first few millimeters of the catalyst entrance, you will realize the steep gradients in the total oxidation products, meaning that the complex interplay or the competition I spoke about between total and partial oxidation does exist. Now, what we did as the first step, remember we wanted to use the effectiveness factor approach that I spoke about. So we just used the single channel monolith and the plug flow model without the effectiveness factor and compared these two. So as you can tell from this graphs here, the CFD model and the plug flow model, they give results that are quite different. And this is because in this case, like I said, we haven't accounted for the mass transfer limitations, and our concentrations have not been corrected, hence this discrepancy that we observe. So now we realize that indeed there is this significant difference. And now came the inclusion of the effectiveness factor to check now what happens when we include the effectiveness factor to correct for the reaction rate. Now, in this case, in the isothermal case, you will realize that now, upon applying the effectiveness factor, the mole fraction profiles for both CFD and the plug flow model, now they agree quite closely at the inlet temperature of 473. So this is for carbon monoxide, hydrogen, and oxygen. And what we did was to say, okay, now let's increase the inlet temperature to see whether the agreement will still be close upon increasing the inlet temperature. And in this case, we did increase the temperature from, and then try to observe if in this case, this was the non-isothermal before we increased the temperature. Remember, we did this for two cases, effectiveness factor for isothermal case and non-isothermal case. And even for the non-isothermal case, we realized that upon using this effectiveness factor, there is that close agreement between CFD and the plug flow model for a single case monolith channel. Then we increase the inlet temperature to say, okay, we want to see that indeed this will be general in the sense that it will apply across a wide range of conditions. So at 573, still we can observe that you still have this close agreement between CFD and the modified plug flow model with effectiveness factor. Now, we said, okay, it's about time now that we go to that, the pseudo-homogeneous model that I spoke about. So in a multi-channel monolith, as I've said, you will have a monolith with these thousands of channels, and you're modeling each channel and also the interaction between channels through heat transfer. Or it can be represented in the pseudo-homogeneous illustration, as you can observe here. And in this pseudo-homogeneous, this is where I said you have that linear combination of the two analytical solutions. Now, we therefore said, okay, we want to compare whether if you choose a certain radial position on the multi-channel and the same radial position in this pseudo-homogeneous, will this hybrid model mimic what we observe in the multi-channel case? And remember, now when we come to this, these are just the profiles that we have, temperature profiles in a multi-channel CFD model. And these are what we are going to compare with what will be observed in this pseudo-homogeneous approach upon using those two analytical solutions that I have spoken about. Now, upon doing so, then we used the what you call this would be the ratio between the free flow and the zero flow, and this was used to effect the linear combination as I have shown in the previous equations. And in this case, you'll observe that there is indeed that close agreement between CFD and the hybrid model. And in this case, I chose R is equals to 0, R is equals to 0.5, and R is equals to R for the purpose of this presentation. And in each case, or for any value of R chosen, we did obtain a very close agreement between CFD and multi-channel and the hybrid model, which I have explained. And remember, we did this for temperature and then at different inlet temperatures. And then now when we came here, we also said, okay, we want to change the inlet temperature again. Like you also can tell, it's different from the previous page. And then in this case, the inlet temperature is 573. And in the previous page, it was 598. And check whether still at different conditions, the hybrid model and CFD will still give us a close agreement. And we observed that it did even for more radial positions. I just chose 3 for the purpose of this presentation. Now, we also, remember I just showed you the comparison between just temperature profiles, but we wanted to check whether also this will agree when we look at the species mole fraction profiles. And in this case, I just chose one species, which is carbon monoxide. But in my dissertation, I showed all the species. And even for the species mole fraction profiles at various radial positions, the multi-channel and the pseudo-homogeneous or the hybrid model still show us a close agreement between the two models. And now, what we did was to also go ahead and show, okay, this was for carbon monoxide. We did show for oxygen as well that it still does show the close agreement between this multi-channel, which is represented here, and the hybrid model at a chosen R value in the multi-channel case. Remember, in this case, when you impregnate the precious metal on the catalytic walls, these are quite expensive because the catalysts are from the precious metals. So what I needed to see was to check whether the influence of the degree of impregnation will change, for instance, methane conversion. And this will help you to get the optimum degree of impregnation such that you won't be using more than you need. So what we did was to choose a different catalyst loading here. And then from that, observe the methane mass fraction profiles and others as well. And you'll observe that at 1.45 milligrams per meter cubed and 2.08, methane mass fraction profiles are quite similar. So it does show that indeed, if you choose this 1.45 milligrams per meter cubed as your catalyst loading, it will give you the similar results as a 2.08. And in this case, it helps you to not use more than is necessary, whilst you can use less for same results or same performance. So I showed also the methane conversion and how this is affected by the degree of impregnation or catalyst loading. And still you realize that between 1.45 and 2.08 milligrams per meter cubed of catalyst loading, the difference between methane conversion in these two is quite is insignificant, if I may put it that way. And for my thesis, I've also shown that, remember, the monolith can, how you impregnate it, can change the degree of impregnation along the axial coordinate. Do you really need a long monolith, or even a short monolith can give you the same results? but I didn't include this for the purpose of this presentation. So now the summary of what we have achieved in this was that a modified plug flow model was validated against the single channel CFD model, and that was embedded into a multi-channel simulation for a faster hybrid model. Now the multi-channel monolith has been simulated by the hybrid model, and accurate representation of a 3D CFD model was achieved at a moderate computational expense, as I've shown. And now, when I said this is because the clock time on the Intel R-Core CPU workstation using the hybrid model was 0.53 seconds, which is quite significant reduction in computational cost compared to the 3D multi-channel simulation, which takes an average of 38 hours to obtain a converged solution. And the hybrid model was used to also investigate the performance of monolith reactors over a range of operating conditions. And what I didn't show here as well was we also embarked on the economic optimization of using this monolith reactors. And I thought maybe the presentation would be long if I include all these details. So basically that's it. And I would like to thank also John Smith, they are the ones that funded this project, and also Prof for his guidance in my project, and also the entire group for this seminars that we had, because we did learn a lot from them. And thanks a lot. Now we can hear questions from you.
Thanks very much, Mopeli. Sorry, I forgot to allocate a chair at the beginning. Maybe Dylan, would you kindly chair for us? Sorry, you're on mute there, Dylan.
Oh, sorry for that. Thanks, Mopeli. That was quite an interesting presentation. It took me back to my Chem-Eng days and all the core maths as well. So it jogged my memory quite a bit, and I'm sure it did with everyone else. I'll open the floor now to any questions. So I think we broke it up into a technical bit and then questions on the presentation. Is that right?
Yep.
Okay, cool. So yeah, any technical questions for Mopeli?
Yes, I have a question. Yes. So
sorry, Pilani, you've gone faint again.
right. Can you hear me? Is it clear?
Yeah, now, yeah, we can hear you now.
Yeah, it's a bit better now.
Okay. Yeah, just a question. So yeah, it is very interesting, especially the study of the catalyst loading. And I think it's like a law of diminishing returns. I think the more you add, the less return you get for that increase. I don't know though. It's just a general case. Is there like a rule that we can use to choose? Because I know you said you had one low value. I think it was 1.48, and then 2.08, and then you basically proved that using the higher value doesn't actually give a lot of benefit. But is there like a cutoff? I mean, a formula that you can use for cutting off? This is just general, because in my work as well, I have a similar, I think, law of diminishing returns, where I model based on number of parameters, and then as you increase the number of parameters, your model, the quality of your model is increasing, is better. But then it comes a point where, the more you increase, what you get is very little. So I don't know, is there maybe something that you came across to help, choose when that phenomena happens? I think it's referred to as like a law of diminishing returns. Maybe
no. Okay, I understand your question. So in this particular case, I didn't use like a general form that helps you to achieve that. So I think basically what I did here was just because I had this catalyst loading in my model equation, right? So it was, I wouldn't call it maybe a sensitivity per se, where you had to include various values for this until you got to a point where the increase does not yield any better conversion, right? So I think it would have been interesting, like you said, to have a general method that allows you to calculate that without having to, like I said, include all these many values until we have a point where they no longer change. So I did not use that method.
Okay, and you don't have any idea of maybe so you've never come across any rules, because I know they can have a tolerance, right? Like if the increase is less than a certain tolerance, then you can choose. Because I mean that's what I'm doing, but I just wanted to ask maybe if you thought about it and if you had a solution to that. Because yeah, with my work I have that phenomena where the more you increase something, what you're getting in return is less as you're increasing. Yeah, I thought maybe you had an idea on how to choose in that, but
I think I did that on my, at first, I remember I did not, you remember I spoke about mesh sensitivity, right?
yeah.
In mesh sensitivity as well, you increase the number of cells, but it sort of becomes try and error when you increase. But at some point, I came across a method where you don't have to include as many as possible. There was a method, I think I'll share with you, but
Okay.
I usually use that in mesh sensitivity, but not on this catalyst loading. There was,
Okay.
so I don't know how, if maybe it's applicable to other applications as well.
Okay.
But yeah, in that case, that's why, let me just show you here. If I might move quickly to that slide. Oh, you see, I have creed 1, creed 2, and creed 3, right? So there's a criterion that I used from the literature that helped me, because previously I would just change the measure. You can imagine it takes a long time to do that. You include this number of cells, you check and do that, right? But I came across a criterion where you can just choose this creeds, and then from that, you can quickly get the creed independent or the optimum number of cells, which give you a creed independent solution. I'll share that with you.
Okay. All right. Thank you so much.
Okay.
Okay, cool. Thanks, Falani. Does anyone else have a question? Okay, Prof, go ahead. Yeah.
Thanks. Mopeli, I think one thing that will occur to people is you mentioned about 5 millimeters where all the action is happening, right?
Yes, Prof.
And your monolith is on the order of 30 centimeters long, right?
You are correct, sir.
So maybe you could unpack that for everyone. Why is it that you've got such a long channel and all the action happens in such a small space? And actually, I'll just admit here that I only actually kind of came up with an answer while you were presenting this. So it's something we never talked about during your PhD. So I'm kind of this is my last chance to put you on the spot. So this is yeah. So let's see if you can, what you say there. Yeah.
Okay. If you remember, towards the last chapter of my my dissertation, I did show, because in this case, instead of increasing catalyst loading, I investigated what if you impregnate only maybe 10% of the total length, 20%, etc. And this helped to answer that you don't really need a monolith that long. So I did this towards the, I think it was the last chapter, where, because the other examiner had asked why I used such a long monolith. So I demonstrated that, yeah, we don't really need this long, because if you impregnate, for instance, up to 5 millimeters of the monolith, then if you impregnate 10 millimeters, going forward, it makes no difference at all to your results. So I think I should have included this as well to show that we didn't need this long monolith.
So what you've said there is true, but I don't think it's the answer. I think if you think of it, think of this monolith as a catalytic converter, right? And someone's going to buy a catalytic converter and install it in their car, and now after and your everything is completely combusting in that 5 millimeter gap at the start, but also the catalyst deactivates over time and it cokes and all that. So the active zone then shifts to the next, so it's like one zone gets depleted and then the active zone kind of shifts along the tube. So, so that you don't have to keep changing your catalytic converter every other day, you can have a moving sort of active zone across your. So that's just my just something I thought about. Do you think that's true though? It's just something I came up with.
Yeah, I think it's true because if the catalyst deactivate, like we have said, in the first 5 millimeters that we spoke about, then we can still shift your active zone to the rest of the monolith channel. So I think it's a clever idea that I never thought about.
Prof, if I can just chime in there, I hope Mopeli doesn't mind. I know it's true because I got marked down for that in design because the trickle bed reactor, we had a similar situation. The optimum length was like about, I think, 4 point something meters, but most of the reaction was happening within like less than a meter. And they asked us why is it 4 meters? Like the maths show that was the optimum length and we couldn't explain why. And after we got marked down, they told us that that's why, because of the migration of the zone, because towards the beginning, you'd have more products eventually than reactants. So the reverse reaction would be promoted. If only I knew that before they asked me the question.
Okay. Oh, thanks a lot for that.
Thanks, Prof. Anyone else have any questions? I see a few people have their videos off, so just unmute if you've got a question. Raise your hands.
I go.
Yeah, go today.
Thanks, Delencha. So my question was, when you modeled, you spoke about 2 frames of reference sort of in your modeling, the macro scale and the micro scale. And you said, I think on the micro scale, you had the 2 analytic equations which you helped, which you used in your model to kind of make the model viable on that scale. Now, with those 2 equations on the discretization, I know if Zamishka was here, she would chime in as well, but Sid can definitely vouch. The discretization process, I know, is a painful one, and especially the number of variables you would have had is not so easy. So how do those 2 analytic equations help you with your micro model?
Okay. I remember as I said, you would think of this as a heat transfer problem because you don't have the heat transfer across channels, right? So what I did in this case, the analytical equations that were very important in this scale were the heat transfer across the channels, right? So you have the free flow that I spoke about, which is the heat transfer on the gaseous phase, right? And you have also heat transfer on the catalytic surface or on the walls, right, from one channel to the rest. So those are the 2 equations that I combined together. And then upon combining those 2, then remember I took those and then I employed in the linear combination, I employed what I said, the beta, which is the ratio of the free flow to the zero flow. Then I took that answer and then embedded this into remember I spoke about a single channel monolith, right? A single channel monolith, as I have said, does not take into account the interaction between the channels through heat transfer. But when I had those 2 heat transfer equations that were linearized in the way that I've done, then I was able to take that and use it in the the modified plug flow model, right? So in this case, it was able to give me the result that I had because then it had accounted for the interaction that I spoke about through channels, right? Because if you have the pseudo-homogeneous approach that I spoke about, but you don't have the linear combination of those 2 analytical solutions, then it won't give you the correct temperature profiles.
Yeah.
So it did help me in that fashion.
Okay, cool. Thank you. Thanks.
Thanks, Sid. Anyone else have a question?
Yeah, if I could also just chime in. Mopeli, yeah, I know you from third year, and I'd just like to say, like I'd like to pass my condolences to you. I think the fact that you finished your PhD, even though you've experienced loss, it bears testament to your character. So you're an inspiration to us all. In terms of your PhD study, like I think it's very clear that with open source software, I mean the biggest obstacle is that there may be documentation, but you really have to study it on your own. You can't, it's not like applying modules and not getting a fine-grained understanding of it. And I know that you've done that. So in terms of the framework that you've created, could your study and your framework that you've created be then how can I say, be used for another catalyst? So for instance, maybe there's another application. Is it just as easy as changing the reaction or all the reaction kinetics so that the study if you're doing this as a project, it can be used to determine or conduct a study for a company, for cost optimization for another catalyst? Yeah, is it as easy as just changing the reaction kinetics and then conducting the study and then giving them a report saying, okay, for this catalyst that you have, here is the report? Because I would assume maybe it's as easy as that, because you've basically, well, from my perspective, covered all aspects of I think not even reactor fundamentals, but as you go further, like postgraduate studies. So is it as easy as that?
Okay, yes, it is, because even in this case, if you go back to the reaction mechanism here, if you were to use a different catalyst, in this case, we're using platinum, right? So if we were to use a different catalyst, but for the same process, you will still have just change the reaction mechanism, right? And you take this, then apply it to the surface reaction rates, right? So it wouldn't be much of a problem. Maybe if you asked for a different process, would it work for a different process? But for different catalysts, for partial oxidation, you can employ this for various catalysts. And also remember, this was for partial oxidation. I think I tried a few simulations on total oxidation as well. So I was able to use this for that as well. So in terms of catalyst, you can use as many as you want by just coming here and modifying your reaction kinetics. And applying.
Yeah, that's great.
Yeah,
it's great work, especially when they come up with these new catalysts. This is a great resource for future researchers, for even companies. So yeah, good work.
Sorry, can I comment on that?
Yes, Prof.
So something to realize here is that we used that CFD, those routines, those open source routines, we used that as the kind of experimental setup. It was more for experimenting, but the hybrid model that Mopeli developed, that doesn't require CFD. Or even though there are some parts to that where you may need to solve PDEs, but you no longer need to solve a full CFD in Mopeli's model. So that means that you no longer are reliant on that whole model. And so you don't need CFD anymore, right? That's in a way the point of Mopeli's thesis, that now you have this super fast way of solving equations of this type. And so in fact, we ran into IP issues, or I'm not sure whether IP is the right term, but yeah, maybe Mopeli, you want to touch on some of the challenges we had with the people who had produced that open source software, because while Mopeli was doing this, I think they decided they didn't want it to be open source anymore. And then yeah, there were some difficult emails that we ended up having to write. But you see, the advantage is that after Mopeli developed his model, it's no longer necessary, it's no longer dependent on that CFD model, and now you've got this blazing fast model that solves in half a second. So yeah, maybe that's just to give you an opportunity to elaborate on that, Mopeli.
Oh, okay. I thought because he had spoken about the open source model, so I thought maybe he was asking it in the context of this open source CFD code. But yeah, when it relating to the hybrid model, yes, it can be applied across various processes and different catalysts because, like I said, this was just a benchmark and numerical experiment, the CFD code. So we don't necessarily have to come back to CFD because we use this, we validate, then once we have validated, it means that we can use our model independently because it extrapolates well and it's very general in its predictions. So it can. Now, regarding what the Prof spoke about on the IP issue, remember these are the people that I communicated with when I first started working on this project. So I think when they realized with time that they could make money out of this, they stopped making it free. So when I was communicating with them, then they said, no, at least they can allow me to use this one. But the other, of course, they had agreed in the first place. So they couldn't even sue you for that because there were emails where they had given me a go ahead to use this because it was free and open source, but they changed later on. But yeah, to answer you, yes, we don't need this CFD code anymore. We can directly employ the fast solving hybrid model in predicting whatever we are asked to do.
Thanks, Mopeli. I think in the interest of time, we've only got a minute or two left, so we'll probably just wrap up there. Just again, from my side, I'm sure on behalf of everyone, congratulations again. It gives us all that motivation to keep pushing till the end, so thanks for that. And yeah, I'm sure if anyone else has more questions, they're welcome to email you or get in touch. So thanks everyone for the seminar. I can hand back to Prof now.
Okay.
Great. Thanks very much, Dilansha, and thank you so much, Mopeli. Our sincere congratulations to you. Yeah, the reactions don't do it justice, so I'm just going to clap to my mic here. Yeah.
Oh, thanks a lot. Now COVID happened. Maybe I would come here and I would come there and celebrate with you, but unfortunately I can't.
Yeah. But after lockdown and all that, we must definitely make a have a time for a get together and maybe let's all go somewhere like we used to do before lockdown and celebrate in person properly.
Yeah. All right, thanks, Paul.
Yeah.
Okay.
Okay, so once again, thank you very much, everyone. Yeah, we'll keep the discussion going. So Mopeli, still don't be a stranger. You are always part of the group, so do attend our future seminars as well.
Yes, Prof. When I'm free, I'll certainly do. I think next week I'll be free again, so I will join you.
Okay. Great. Thanks very much. Thanks, everyone. Bye then.